Recapping where we are a little bit, recall that in studying the direction field and phase portrait of the linear system of differential equations given by y prime equals ay, where y is the vector function xy and a is the coefficient matrix 5, -2, -1, 4, we noticed two straight line solutions. While we have not found those straight line solutions yet, we observed that along a straight line solution, y prime equals lambda y. Since y prime, the direction of the tangent vector, is going in the same direction as the position vector y, so they must be constant multiples of each other. And thus, since ay equals y prime from our differential equation, and y prime equals lambda y for straight line solutions, we have that ay equals lambda y. And this led us to the idea of an eigenvalue lambda with eigenvector v, for which a times v is equal to lambda times v. Moreover, for this particular matrix A, we found the eigenvalues and eigenvectors. They were lambda 1 equals 3 with eigenvector 1, 1, and lambda 2 equals 6 with eigenvector -2, 1. Notice how these eigenvectors 1, 1 and -2, 1 line up with the straight line solutions that we were seeing in our phase portrait. But what about the other solutions we see in the phase portrait? We will need two more theorems to find the general solution and understand all of the solutions. The first theorem that we will need is the principle of superposition. We saw this for second order differential equations as well. It states that if y1 of t and y2 of t are solutions to a linear system of differential equations y prime equals ay, then for any constant c1 and c2, y of t equal to c1y1 plus c2y2 is also a solution. That is, any linear combination of solutions gives another solution. This can be quickly verified using the linearity of the derivative and matrix multiplication, though we won't do that in this video. But using this, we can build a collection of new solutions from ones that we already found. But how do we know when the collection of solutions is not just a family of solutions, but the general solution, all of our solutions? For that, we'll need one more theorem that states that if y1 through yn are solutions to a linear system of n differential equations, y prime equals ay, and the set of vectors y1 at t0 through yn at t0 at some value t equals t0 are linearly independent vectors, then the linear combination y of t equal to c1y1 plus c2y2 through cnyn forms the general solution. And in the case of two-dimensional linear systems that we've been focusing on, if we can find two solutions y1 of t and y2 of t that are linearly independent, then the general solution is the linear combination c1 times y1 plus c2 times y2. So what remains to find the general solution is being able to find two linearly independent solutions, y1 and y2. Understanding these straight line solutions will be the key to finding these linearly independent functions y1 of t and y2 of t. Because if A has distinct eigenvalues lambda 1 not equal to lambda 2, then we saw that the eigenvectors, and thus the straight line solutions, will be linearly independent. So we will be able to build the general solution from them. Our next steps will be finding y1 and y2, the straight line solutions.